So welcome to this webinar. Today we're going to talk about BTS SPORTLAB and in particular the new jump protocols package. Here with me there's Matteo, with engineer Matteo, who is part of the customer care and installation training team, and is also expert in sport biomechanics. So Matteo, the stage is yours. You can start whenever you want, and see you later.
Thank you. Thank you. Hello. Hi to everybody. Okay, let's have a look at this jump protocols package for the BTS SPORTLAB. Okay, so let's introduce the BTS SPORTLAB. Of course, the study of the movement is an important tool that allows a quantitative measurement of the physical and biomechanical features of professional and also amateur athletes. Thanks to this objective information, the sport medical staff can plan customized training programs that are aiming at, of course, enhancing the sport performance, identifying any possible weakness in the athletic preparation, and, of course, to reduce any injury risk related to the sport. The SPORTLAB is a powerful, modular, and scalable solution based on fully integrated equipment. It is the only system, in fact, that provides a native integration of kinematics with infrared cameras, of course, kinetics or dynamics with force plates, and electromyography, all in one system, in one device. Okay. Okay, so BTS SPORTLAB allows the planning of customized training program based on in-depth knowledge of the actual potential and condition of each individual athlete, avoiding any risk of overtraining and allows to improve the performance. Okay, the BTS jump protocols are a part of the objective examination of the athlete and allow the quantitative assessment of the jump movement. What do we see with the analysis of a jump? We see the dynamic parameters, the kinematic and inverse dynamic parameters. Inverse dynamic is, let's say, obtained by combining dynamic and kinematic measurements, and the muscle activation and the timing of the muscle activation in respect to the jump in this case. Okay. How it is composed, the BTS SPORTLAB is composed by infrared cameras that track the movement. So they basically track the kinematic part. So the infrared cameras work for the kinematic part, so the study of the movement of the athlete by putting on reflective markers on the body of the athlete. The force plates give info about the dynamics, so of course the ground reaction forces and torques that the subject exchanges with the ground, okay, during the jump. The MG probes, as I was saying before, they give information about the muscle activation, so how much the muscle is activated during the jump and the timing of activation in respect to each phase of the jump that we will see soon. The video cameras instead are just video cameras, let's say normal video cameras that are used in order also to record a video, no? Let's say a normal video of the subject performing the task, so that the coach or who is, let's say, using the system can also see visually, let's say, how the jump was performed and so on. Okay, so all these hardware that we saw before gets all the information. They are all synchronized, of course, all the devices that we saw before, they're all synchronized and integrated automatically by our software. Evo Capture is called, and for example, here you can see both a screen of the software of how it looks And also, of course, it gives out a personalized report with all the information needed. Okay, which type of jumps are included in our protocol package? The counter movement jump, both bipodalic and monopodalic. The repeated counter movement jump, so at least, let's say, 6 in a row, but even more. Repeated vertical hops. So the difference here is that the vertical hops are jumps in order to calculate, repeated jumps in order to calculate the leg stiffness, the leg vertical stiffness. So the subject is jumping with the minimal flexion at the hip and the knee, and mostly flexing the ankle. Drop jump, both bipodalic and monopodalic, and also the squat jump. Okay, let's say that today we are looking at all the procedure and so on for the counter movement jump protocol, because let's say that the rest is very similar, just a little things change, like some events and so on, but let's say everything almost is the same. So yeah, just to keep it a bit shorter, we show this one. Okay, so the subject preparation. Okay, this is a video, and we see how the subject preparation, so how to place the markers and the EMG on the subject.
The counter movement jump protocol uses a total of 30 markers for the standing and 22 for the jump. 3 markers must be positioned on the subject's trunk in correspondence to the 7th cervical vertebra and by the right and left acromion. In the pelvis, you have to identify the position of the 2 anterior superior iliac spines, ASIS, through palpation and place 1 marker on each of them. Apply also 1 marker on the back in correspondence to the 2nd sacral vertebra. Start placing the marker in the middle point between the 2 dimples, identifying the lumbosacral passage. Finally, place 2 technical markers below the 2 posterior superior iliac spine. The sacrum marker must not be in line with these 2 markers. On the lower limbs, place a technical marker for each thigh at about 4 fingers above the knee. Then, identify the femoral condyle and perform a passive flexion extension of the subject's knee. Once the flexion extension axis has been identified, find the point where the axis passes through the lateral part of the knee. Place 1 marker on the lateral aspect of the knee, flexion extension axis just identified, and 1 on the medial side at the medial condyle. Place 1 marker on each shank. This is a technical marker, therefore it does not require precise anatomical positioning. Place markers on each lateral and medial malleolus. On the foot, place 1 marker in the space between the heads of the 2nd and 3rd metatarsals, and 1 on the heel. These 2 markers must lie on the same plane. Other 2 markers need to be placed above the head of the 1st metatarsal bone and above the 5th metatarsal bone. The last foot marker must be positioned laterally to the foot. This is a technical marker and is used for higher precision during 3D reconstruction. After standing, when evaluating the athlete during the dynamic phase, it is sufficient to remove some of the medial markers. Specifically, the 2 axes of the pelvis, all medials of the knee and malleolus, both heels, and the middle metatarsal. The complete list is given in the manual. The final number of markers for dynamic analysis is 22. Let's now proceed with the probe's application. For the vastus medialis, place the probe at the distal quarter of the line from the anterior superior iliac spine to the medial side of the knee joint line, following the direction of the muscular fibers, slightly oblique. For the vastus lateralis, place the probe on the muscle belly, halfway along the line from the anterosuperior iliac spine to the superior pole of the patella, following the direction of the muscle fibers. For the biceps femoris, place the probe at the distal 1/3 of the line from the ischial tuberosity to the head of the fibula. Finally, for the semitendinosus, place the probe at the proximal 1/3 of the line between the ischial tuberosity and the medial epicondyle of the tibia.
Okay. Okay, in this video, we'll see all the recording phase. So after the subject preparation, let's see how do we do the acquisition of the static and the dynamic trial.
From the software interface, we create the patient profile by clicking on New Patient and filling in all the mandatory fields, namely first name, last name, date of birth, and gender. Then click Add Patient. We then create a session by clicking New Session, typing in the session name, and creating the pathology if necessary. We select the protocol to be used for acquisition, in this case the jumps with kinematics and dynamics protocol. Enter the anthropometric measurements. Then click Create Session. First, you need to acquire the static position of the athlete. Click on New Trial and select Standing, and then Acquire. Select the devices needed to acquire the test. In this case, the infrared cameras for kinematic analysis and force plates. Now ask the athlete to step onto the force plates and stand still for about 10 seconds to acquire the static position. When the subject is ready, click Monitor and then Acquisition to start the acquisition. When the trial is finished, click the Capture button again to stop the trial and save it. Notes can be added if necessary. Before starting the acquisition, medial and technical markers need to be removed from the subject, as described in the manual. Now, acquire the jump by clicking on the Session and New Trial. Choose Counter Movement Jump and click Acquire. Now associate each EMG with the muscle to which it was applied. First, name the protocol, for example, jump, and then select the muscles you want to analyze. We opted for the vastus medialis and lateralis, biceps femoris caput longus, and semitendinosus. When the setup is complete, save. For proper execution of the test, the subject is asked to stand on the force plates in an upright position. The subject should perform the jump starting from a neutral position that must be held for at least 3 seconds before starting the movement. When the subject is ready, click on Acquire to start the acquisition. When the trial is finished, click the Acquisition button again to stop the trial and then save the trial. Finally, acquire the MVC trials, one for each muscle district, by clicking on the Session and New Trial. Choose MVC trial and click Acquire. To acquire the MVC, it is necessary to refer to the rules and machinery for evaluating the maximum voluntary force of the muscle districts. In the case, it is necessary to acquire the MVC of all the body districts of the evaluated muscles, so knee extensors and knee flexors.
Okay, so let's explain a bit more this part about the MVC acquisition. Of course, the MVC acquisition, you can do it before or after acquiring the jump and the standing and jump trial, actually. Of course, you need to have the EMG probes applied already on the subject, because you need to acquire the MVC trial in order to record exactly the maximum voluntary acquisition value for each muscle that we use in order to normalize then the muscle activity during the jump, of course. In order to be able to compare right and left, you need to do this. Let's say that it's better, of course, if you have the correct machines in order to perform the MVC of each district. If you don't have them, maybe you can do, let's say, for example, the Nordic hamstring exercise for the hamstring, and another exercise about the knee extension for the quadriceps, of course. Better for sure if you have the machines so that you can have a more reliable data. Okay, let's see the next video. Okay, here this video is about the tracking process. So after you acquire the trials, standing and of the counter movement, we need to track. So we need to we reconstruct in 3D the trial, the kinematics, let's say, so the marker's position, and we assign a name, a label to each marker, so that the model knows which marker it is, and can reconstruct the model.
Once the trials are acquired, they need to be tracked to assign a label to each marker and ground reaction force, and reconstruct the movement in 3D. Select the session containing the acquired trials, and double-click on the session to automatically move the trails in the Trials to be Tracked window. Then, click on the button on the right to start the tracking. Using the model on the left as a reference, assign to each marker and ground reaction force the corresponding label. To do so, click on a marker or the force vector and assign the correct label. Remember that to be able to analyze the jump trial, you need to track both standing and jump trials. Once done, click on Save and OK. The procedure needs to be repeated for each trial. So assign again the labels to each marker and ground reaction force, and save the tracking. After the tracking, the trials will automatically be transferred to the window called Trials to be Processed. The processing allows the definition of the temporal events that are needed to define the movement cycles inside each motor gesture. From the right side, select the Counter Movement Protocol from the Calculation Protocol panel list, and click on the button on the right to start the processing. Automatically, a window for the selection of the temporal events will appear. In the title of the graph, you can read the event to be defined. In the title of the window, you can read which trial the graph is referred to. For each movement, define the movement start, so select the frame before the beginning of the movement. Define also the end of the movement, so the frame when the jump is over. Click on the chosen point, and then click on OK. Save and close.
Okay, so we saw the tracking and processing actually phase here.
Once the trials are
yeah, now it's about the creation of the report of the reports about the three let's say data sets. So dynamic, kinematic plus inverse dynamics, and EMG.
Finally, the trials are now in the last window, and they are ready to be transferred to the final report. For a complete analysis of jump using inverse dynamics and EMG analysis, 3 different reports need to be processed and created. Click on the button to open the first report, the kinematic and inverse dynamic report. Immediately, the software shows the report preview, where you find one page with all the information for each movement performed. By clicking on the printer button, it's possible to print the report or save it in PDF format by using the virtual printer. The second report that needs to be created is using the same processed data and gives only the kinetic analysis. Now, in order to analyze the muscle activity during the jump, the trial needs to be reprocessed using a dedicated processor. To do so, select all the MVC trials acquired and process them with the protocol Compute MVC4, right 4 left. It will automatically calculate the MVC value for each muscle. When the processing is finished, click on Save. The MVC trials will move to the next step, Trials to be reported. Then, select again the jump trial. Move it directly from the Trials to be reported section to Trials to be processed by clicking on the blue arrow. Here, select the calculation protocol Counter Movement Jump plus EMG to process the EMG data of the same jump. In this phase, the jump events are already saved for the previous processing, so you will just need to confirm them by clicking OK. The jump trial will move to the Trials to be reported. Select it together with the MVC trials, and then report them using the Counter Movement Jump plus MVC report. This is the final report of the jump analysis.
Okay, so let's maybe explain this a little bit again. So let's say that with the first processing that you saw, you process, the processor is called counter movement jump K plus D, which means kinematic plus dynamic. And exactly, you process all the data about the dynamic, so the force platforms data plus kinematic and inverse dynamics. So by processing the file with that processor, you can obtain 2 reports, the one about the dynamic and the one about the inverse dynamic. Okay, in order to get instead the report about the EMG data, you need to process the MVC trials that the dedicated processor will automatically calculate the maximum values of activation, so the MVC value for each muscle. Then you will need to reprocess in the way that it was showed in the video the trial that has already been processed, but with a different processor, which is the EMG processor, in order to calculate all the data relative to the MG part. So in case this, let's say, allows you to maybe if with one subject you don't want to study, let's say, the kinematics, you are interested only in dynamics and EMG, you can use that processor. Instead, if you, I don't know, in a subject you don't want to study the muscular activation, you just process the one with dynamics and inverse dynamics and so on. kinematic and inverse dynamic and so on. Okay, so now let's have a look at the composition of the report. So the report, as we were saying, is generated automatically. So let's have a look. Let's say that it has three parts, as I was saying before. The dynamic part, so it's all about the ground reaction forces. The kinematic and inverse dynamic part, which combines dynamic force dynamics, so ground reaction forces, with the kinematic, so the markers, basically the markers position, joint angles, let's say, and so on. And the third one is about the EMG. Okay. So let's start from the dynamic part, which is, let's say, the most important one, because with the jump, all the events are defined using the force plate signal. So each phase of the jump that we will explain now, it is essential to have the force plates, that you always need to acquire them, because they are the ones that define all the events and so on. So let's start from the report about the dynamics. So let's say that the jump is composed of these 5 phases. So of course the standing phase before and after, and then we have actually the unweighting phase, which is in blue here, is when the subject starts moving down. The very first part, when the subject starts moving down, so he starts flexing his knee and moving down. When does it end? It ends when he reaches the maximum downward velocity. So let's say when he's reaching the highest velocity going down, so in this case it's negative, let's say. Then he starts using his quadriceps mainly in order to, in eccentric contraction, in order to slow down this movement. And so it's called the braking phase. Okay, the braking phase starts when you see that this is the force graph. This is, okay, as it's written, displacement, vertical displacement of the center of mass, vertical velocity of the center of mass, vertical force normalized over the body weight. This flat line, in fact, is the body weight, and the vertical power. All of these are synchronized, all these graphs, and are cycled between 0% at the beginning of the jump and 100% when the subject is completely stable again after the landing. Okay, so we were saying that the braking phase is when the subject is braking exactly his movement downward, and when he reaches the lowest point of the counter movement, of course the velocity goes to 0, which is here, and he starts the propulsive phase. Okay, so he starts the concentric phase, so he starts extending the knees and start the hips and the ankles and so on, and he starts the propulsive phase that will take him to the flight phase, of course, which is this, let's say, purple one. And then we have at the end the landing phase. This is just to explain a bit the phases. So for each phase we share the duration in milliseconds of each phase, and also the percentage of duration of that phase in respect to the total percentage of the duration of the jump, so from 0 to 100%. And also we have some time to peak force, so time from the beginning of the movement until it reaches the peak force, until she takes off, until he lands, and until he gets stable again, so the total duration of the jump. Okay, so here we have some data about the performance. So downward displacement, how deep was the counter movement. Flight height calculated with the time of flight, time of flight rule, and also the maximum height reached by the center of mass calculated with the double integration of the acceleration, which is, it gives, of course, different results, but maybe someone uses one or another, we give both. We have the velocity, so we give data about the peak of propulsive velocity, so positive velocity, and the velocity at the top, which is the velocity that basically let's say that the height of the jump depends on the takeoff velocity. So since it's impossible to have the same velocity at the top, same as the peak of propulsive velocity, because let's say biomechanically it is impossible, it will always be lower than the maximum, that is this one here. So since the top velocity can't be, as I was saying, exactly the maximum, we try to be as much efficient as possible and try to lose as less velocity as possible in this phase. So the drop of velocity with this value here is in percentage how much velocity you lose from your peak to the takeoff. So the lower is this value, the better is the coordination of the athlete and more efficient the jump. Okay, here we give other data about mean and peak force in each phase. Okay, it's pretty easy. Let's say in Newton, and also normalized on the body weight, where it says BW is normalized on the body weight. RFD is important, is the how fast we manage to increase the force. Okay, so it gives us an idea of the higher this value, it means that the subject is more efficient and in generating more force in a shorter time, so it's more explosive. Let's say that in the counter movement jump, this value is not calculated in the propulsive phase, but just in the braking phase, because in the counter movement jump is looking more at the braking phase for the RFD. Let's say it's more important in the braking phase, because ideally you should reach the peak of the force exactly at the end of the braking phase, so at the beginning of the propulsive phase. And so after that, the force in theory should only decrease until it reaches zero. Of course, it's not always like this, but let's say that ideally all the how do you say, the increase in the force should be just in the braking phase. Okay. Then we have the impulse, which is the area. The net impulse is the area that is between the curve described by the force, okay, and the line described by the weight of the person. So in this area is calculated the impulse, so it's a measurement that is in force multiplied by seconds, by time, and it gives an idea of how much force the subject has in total, can generate in total in the braking phase and in the propulsive phase. So the RFD and the drop of velocity are index about coordination, while the impulse is an index about how you distribute your force between braking and propulsive phase, and also how much force in total you can express. And the impulse ratio is the ratio between the propulsive impulse and the braking impulse, exactly to give you an idea about the strategy. The impact ratio instead is the ratio between the force at the impact, so at landing, divided by the force at pre-jump, the maximum force at pre-jump. The leg stiffness tells us if the leg stiffness is very high, it means that the subject at landing is not absorbing much. And so it means that we have, it doesn't, let's say, flex too much to absorb. And so, let's say the impact force will be bigger. Instead, if the value is lower, it means that he is basically flexing on his knees, on his hip, and on his ankle in order to absorb more of the impact force, and the impact force will be lower. Here we have, let's say, the symmetry analysis between right and left forces in the standing position.
Sorry, Matte.
Yeah.
There's just one question regarding the previous
Yes.
page, so I just wanted to do it before like moving on.
Yes,
one person here is asking something about the flight height. What is
Yes.
the value of jump height? 23.29 centimeter or 30.45?
Okay.
I think the 30.55 is the maximum height.
Yes, let's say that they are it's two different calculations in two different ways. So let's say that, for example, the flight height considers how much you jump from the moment you take off. But in the moment you take off, imagine that also the foot is not flat, the foot is already, let's say, extended. And so also all the knees and the hips are extended. So you are taking off from a higher height. Instead, the other one is how much you jump from when you are in the orthostatic position until when you reach the maximum jump. So it depends on what you want to see, let's say. They are both valid. I don't know how to, it depends which measurements you want to see, let's say.
Thanks. Sorry for interrupting.
Okay, thanks. Okay, so the next one. Yes, we were talking about the symmetry analysis. So here we see the same parameters that we have in the previous page, but in the symmetry between right and left. So here we have the vertical force, then there is the anterior posterior force and the medial lateral force. Green, all the green forces are right and all the red forces are left. Exactly. So we see that if we look exactly, let's say at the vertical force, the green force is higher both in the pre-flight phase, the pre-jump phase, and also the impact. So we see that, she's basically putting more force both at landing and at in the pre-jump on the right leg than in respect to the left. Okay, here is other pages about the kinetic report. We have the power analysis, so the power generated and absorbed. So generated is in the propulsive phase and absorbed in the eccentric phase or braking phase. And here is the total power. And here we have again the symmetry between right and left power. Okay, again you see that maybe this graph is a bit small, but you can see that the green line, the green power, so let's say the power of the right leg is much higher, both in generation of power and absorbing of power, let's say. Same as for the force. Here we see the center of pressure analysis of both the right and the left foot before and after landing, so that you can see if the subject more or less take off and lands on the same place, let's say, or if it's moving a lot, maybe on one side or another, or forward. It gives you an idea again of maybe if it's unbalanced in some way. In this case, the subject was pretty much stable. Okay. Here we have some screenshots taking exactly the events described. So start of braking phase, start of propulsive phase, peak of propulsive force, and when we have the highest force at the landing. What we can say is that, okay, basically we are just reporting the same values that we saw in the previous page, but here you can also see exactly how the subject looked during each event, which is very important, both on the sagittal and also on the frontal plane. And soon we will be integrating the new podium, which basically will allow to overlay the force vectors, right, left, and also the resultant over the subject, so that you can see if the ground reaction force is where it is passing in respect to the knee joint, medially, laterally, and so on. It will be ready soon. Now, when we took these trials, it wasn't ready yet, but it will be ready. So you don't see it here, but it will be ready soon. Okay, instead, this is the inverse dynamic report. And here we have basically the comparison of, okay, so in the first two graphs are the joint angles. So pelvis is in blue, hip, ankle, hip, knee, and ankle. Ankle is, let's say, the continuous line, and then knee and hip have this, let's say, different style of the line, and we can see here the joint angles on the flexion extension planes on the sagittal plane for all these three angles. In green, we consider the right leg, and in red, the left leg, so that we can see what is the coordination inside the same leg between these three angles, these three joints, let's say. So we can see, for example, here that the first one to extend is the hip. Shortly after, let's say that, sorry, to flex. Let's say that the positive angles here are flexion and the negative angles are extension. So we can see that who reaches first the maximum flexion is the hip, shortly after the knee, and then the ankle at the latest one. So that this allows us to understand the coordination inside the same leg. Here we also have the joint moments, so the internal moment that the subject applies during the movement. Okay, so in this case, the graph is, let's say, the contrary, the opposite. So we have extension as positive values. In fact, you see that at landing, we are applying, let's say, big extension torques in order to absorb the impact, of course, in eccentric contraction. And also, for example, we see that the knee is in the braking phase is of course putting a big extension torque in order to slow down the movement, the downward movement. Okay, if we look at the joint powers, positive means power generated, negative means power absorbed, so that we can see, for example, in the braking phase, the knee is absorbing a lot of power, and then in the propulsive phase, all of the joints are generating power. The hip it generates much less power, than the knee a bigger power, and the ankle even more. The ankle is the last one to generate power because it's the last one that let's say extends. And here in the other page we have the same graphs as before, but here we compare right and left, so we can have an idea about the symmetry. Again, right and left, some interesting values. at some the peak and the values at some events. So here we have the joint angles, hip, knee, ankle, the joint moments, hip, knee, ankle, and of course also the power. Here we have some graphs, some table about work absorbed and generated from each joint for the right and left leg. And here we have the same, but as a percentage of that leg. So the hip absorb 1.3% of the right leg. The knee absorbs 93% and the ankle, let's say 6% of the work absorbed from the right leg. Of course, same for the left and for the generation of power. Okay, here is the page about the MG. We have basically the comparison between the vastus medialis right and left, vastus lateralis right and left. So the quadriceps and then the hamstrings the same, bicep femoris, semitendinosus. So in each of these table, we show the mean value of that muscle for right and left in the eccentric phase in respect to the MVC, the peak, the time at which the peak happens in milliseconds and in percentage of the total jump. And here you see when the peak of force happens, so that you can compare the timing of the muscle with the timing of the force. Yes, and here you have also some values about the value of the MVC in microvolts, if it can be interesting. And finally, on the last page, we have the symmetry analysis. So how do we read this page? We have vastus medialis contribution, right and left. Vastus lateralis, right and left. And we see that, for example, vastus medialis in respect to the vastus lateralis for the right leg is 48 against 52, for example. Same analysis for all the other muscles. Here we have the hamstring, bicep femoris, semitendinosus, same thing. And here we see that if this value is red, it means that the stronger muscle in this phase was the left. If this value is green, it means that it was the right. So it means that in the hamstrings, she was using much more the right ones than the left ones in the breaking phase. Actually, in every phase we see here. While for the left, for the quadriceps, we see that the situation was more balanced because, okay, in the eccentric phase, it was using more the left ones, but then in the propulsive, it was more or less balanced. The bigger this line, let's say this rectangle, the bigger the difference, okay? And so on. Here we have a graph about, let's say, the hamstrings quadriceps ratio. So we measure the activity of the hamstring divided by the activity of the quadriceps in each of these phases for the right and the left, and we provide the value. So if the value is high, it means that she was using much more so let's say, if the value is 1, she was using in the same way hamstring and quadriceps. If the value is less than 1, she was using more the quadriceps. If the value is over 1, she was using more the hamstring. So this is to have an idea how she's working in this way, how she's balancing between her hamstring and quadriceps. Okay, do you have any question?
Do you have any questions? Yes, we already have some questions. So Paul is asking is the RFD calculating in the braking phase or in the propulsive phase?
In the braking phase. for the counter movement jump. In the squat jump, instead is in the propulsive phase.
And is also asking how is the leg stiffness calculated?
The leg stiffness is the force, the peak of force at landing divided the displacement of the center of mass at landing.
Okay.
So let's say maybe, yeah. So it's basically the peak of force here divided the downward movement at landing.
Paul is saying thank you, Matteo.
Thank you, Paul.
Thank you too. So do you have any other questions regarding the protocols, the jumping analysis, the very detailed report that Matteo explained? If you want, you can also send questions to us by email, and then we will answer privately. So here there's one other question. Do you have normative values for different calculations, such as RFP, impact impulse ratio, peak power, etc.?
We don't have, but let's say that it's possible to create your own normative data with our software if you acquire a lot of, let's say, subject and so on. But yeah, we don't have because it changes a lot between different sports and so on. So yeah, we don't have that.
Also, it depends on the type of athlete that you are evaluating. If it's
Yeah.
return to play, so after injury, so it depends on the age or any of the sport also. So it is difficult to create like normative values, like values of references, generally speaking, in sport. Where can I find a list that explains how all the parameters in the report are calculated? You ask Matteo all the time. He's here.
We need to. I don't know if it's explained so much in detail in the manual. Now, honestly, I don't remember, but we can check. Or else, yes, we can send you. I don't know. Yeah, we can schedule a call or send you some. Yeah.
Yeah, they're like mainly they are explained in the manual that we give to clients, to customers. But also, if you have some specific doubts about another parameter or a specific parameter, you can send an email to us, to Matteo, or also schedule a call, a meeting with the team in order to get more like deep in the parameters calculation. So far there are no other open questions at the moment. I just wanted to, like, before finishing, just wanted to remind that we will have 2 upcoming events. One in Hong Kong in June, and which is our IRSSD, more about clinical evaluation of posture analysis. And in July, we will participate to ISBS in Salzburg, Austria. So if you're around, just come to visit us and let us know if also this webinar was useful and was interesting for you. We remain available also by email or contacting us also through the website. I thank again Matteo. There are no other questions, so thank you very much for your very detailed explanation of the report. It was very interesting, and see you for the next events.
Thank you.
Bye.